Okay, so looking at brittle and ductile materials with a notch present in the component, the question is what will happen if you strengthen or if you machine a notch into a component? Will it strengthen or weaken the component? So consider the following. If you machine a notch here, so this is a cylinder, and then so there's your notch machined in now. If you compare this with the similar cross-sectional area cylinder on this side, so very important that we compare these two and not a cylinder of that size, the original size. If the material is ductile and you have a notch, then it means that you'll have a stress concentration in front of the notch. And then you will get plastic deformation around the notch when it goes beyond the yield point, which would mean it would actually strain harden it at that point. Therefore, if you then stress it, the material will be stronger than before. However, if you just have a cylinder this size, there would be no strain hardening and it will not give you the same strength. However, if you have a cylinder of the original size, of course, that will give you a better strength than one with a notch. So it's important what you compare. But so if it's a ductile material and you get strain hardening, then you can strengthen it. But if it's compared to a similar diameter. So if only that cross-sectional area is considered at the notch, then the material would be strengthened. Then theoretical stress concentration factors. So this is quite helpful in terms of certain configurations. So for instance, this has a width of W, you've got a hole in there that has a diameter D. And then you can see here is D over W and the stress concentration factor KT, so what you can expect. Then we've got another one here, W, width of W, with this little round semi-circle notches there. It's an H and a B and a B. And then you get different configurations. So all of these are just ways to get a quick answer for your KT, your stress concentration factor, your theoretical stress concentration factor, based on a certain configuration. Now, and there's quite a lot of those, but what is more helpful is if you can do a finite element analysis with typically like software like ANSYS, where you can actually see maybe in these darker red regions, you're going to find that the stresses will be extra high. Whereas in the blue, you'll get low stresses. So it gives you an indication of what stresses to expect where. Now, so up until now, we've discussed the elastic stress-strain conditions, but now we want to get to the point of the yield point. So maybe that breaks over there, and yielding occurs at this point. That's stress and that's strain. So if we do a uniaxial tension test, of course it's easy to determine the yield point, or fairly easy. Sometimes it's more difficult, but What we don't know is if we then go to a three-dimensional stress condition. So it's from 1D to 3D, what is going to be your yield point? And there are two relations, or empirical relations. So important, these are empirical relations, so they're not from first principles. It's basically an assumption that was fitted to it. So the first one is von Mises. And von Mises said yielding occurs when the second invariant of the stress deviator, J2, exceeds a critical value. So it's all about the stress deviator, J2, and J2 is described by this. Now, we have not done that, but there's J2. J2 is equal to 1 over 6 times then the sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. And he said when this is equal to a certain, so the stress variance is equal to a certain constant, and he said it's squared. So however k is unknown and we have to evaluate it. So yielding happens when this reaches a certain condition, so a certain critical value. And we do know of a situation where this will be true, and of course that is at the yield point. So at the yield point, we've got uniaxial tension. So uniaxial tension means at the yield point that sigma 1 is equal to sigma 0. So that will be your yield point. Sigma 2 is equal to 0 because it's uniaxial. And sigma 3 is also equal to 0. And then we just put all of that in there, which is then, of course, this, basically to solve the value of k. So we say k squared is equal to 1 over 6, sigma 1, and so on, it's all squared, is equal to then 1 over 6 times then sigma 0 minus 0 squared plus 0 minus 0 squared plus 0 minus sigma 0 squared. So that is then equal to 2 sigma 0 squared over 6, which is equal to sigma 0 squared over 3, and so k is sigma 0 over the root of 3. And then we just can substitute this value for k in there. And what do we get? Get the following. Sigma 0 is equal to 1 over the root of 2 times the root of sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared, plus then, of course, this was added on, just the influence of the shear stresses. Okay, so we actually only considered the first, but we didn't consider the effect of the shear stress. But von Mises said this, and what this means is when the stress, so you've got a certain stress condition. Calculate the stress condition and it gives you a certain value. And if this value is more, so if it's greater than your yield point, then you know you get yielding. if this value is less than your yield point, then no yielding. Okay, so the example then is the stress analysis of a spacecraft structural member. Gives the state of stress shown below. So we see here sigma z is compressive, 50 megapascal. Sigma y is in tension, 100. Sigma x is also tension and 200. And then we've got a tau xy at 30 megapascal, so that's actually a negative 30 megapascal. But it doesn't matter in this case because it's all the shear stresses are squared. And what is given is it's a 7075 T6 aluminium. It has a yield point of 500 megapascal. Now, this is simple actually to do the calculations, but you have to remember to use the correct sign. So for sigma z will be sigma 3. So sigma 3 is negative 50. Sigma 1, there's sigma 1 because of the largest, is 200. So this becomes negative 250. So just be very careful. And here's the solution. So that's our equation. This is all 0. And then we put that in and calculate, and we get a value of 224. The sigma 0 was 500. So if we calculate the safety factor, it's 500 by 224, gives us a safety factor of 2.2.